So let's start with what an alternating series is. An alternating series is a series in which terms switch between positive and negative signs and are typically expressed as negative 1 to the power of n or negative 1 to the power of n minus 1 multiplied by a positive term b sub n. Next, let's talk about the alternating series test. To determine if an alternating series converges or not, we use the alternating series test, which states that the series must satisfy two conditions. The first is that the terms must decrease in absolute value, and the second is that the limit of the terms as n approaches infinity must equal 0. And if both of these conditions are true, then the series is convergent.
Estimating sums of alternating series. We can use the partial sum s sub n to approximate the total sum of s. The error of this estimate is r sub n, which is equal to s minus s sub n. The size of this error for series that pass the alternating series test is b sub n plus 1, the absolute value of the first neglected term. Warning, error is generally only smaller than the first neglected term in alternating series. This method will not work for other kinds of series. So, if s is equal to the sum of negative 1 to the n minus 1 times b sub n, where b sub n is greater than 0, is the sum of an alternating series that satisfies b sub n plus 1 is less than or equal to bn, and the limit as n approaches infinity of b sub n equals 0, then the absolute value of r sub n is equal to s minus s sub n, which is less than or equal to b sub n plus 1.
So hi, this is Mahir and I'm going to talk about absolute convergence and conditional convergence in this video. Let's go through them. So a series is an absolute convergence series if we take all the absolute values of each of the elements of the series and add all of them together, and the result of that new series is an convergent series. Then we call the main series an absolute convergence series. Let's look at the example here. So in the example, the main series is 1 minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square. This is the main series. Now, if we take the absolute values of each of the elements in this series, 1 plus 1 by half square plus 1 by 3 square plus 1 by 4 square, and add all of them together, then it becomes an convergent series. So now we are calling the main series an absolutely convergent series here. Let's go to the next one. So this is conditionally convergent. So if we take a series and when we add all of them when they are in the normal format and they are a convergent series, but when we take all the absolute values of that same series and we add all of the elements now and it becomes a divergent series, then we call the main series a conditionally convergent series. Now let's look at the example here. So 1 minus 1 by half plus 1 by 3 minus 1 by 4, if we add everything here, it becomes a convergent series. But now we are taking all the absolute values of this series. So it's 1 plus 1 by half plus 1 by 3 plus 1 by 4, and if we add all of them together, it becomes a divergent series. So we are calling the main series a conditionally convergent series. Let's go to the next page. Okay, a series is absolutely convergent, then it's convergent. It's pretty much intuitive. Let's look at the example. So we have cos n divided by n square. So if we plug in 1, 2, 3 in this series, and then we are going to take all the absolute values of like cos n divided by n square, and we'll add all of them, and we can see that it will be an convergent series. And because we are adding all the absolute values, we can also call it an absolutely convergent series. And because the series is like absolutely convergent, we can also call the main series that we had from the previous page and also a convergent series.
Okay, so now rearrangements of series, which is one of the most surprising ideas in calculus. First, any convergent series falls into one of two categories. It's either absolutely convergent or conditionally convergent. And here's the key idea. If a series is absolutely convergent, meaning the sum of the absolute value converges, then you can rearrange the terms in any order, and the sum stays exactly the same. So in that case, order doesn't matter, just like with finite sums. However, things get interesting and different when it comes to conditionally convergent series. These are series that converge but not absolutely, and in this case, rearranging the terms can actually change the value of the sum. Let's take a look at this example over here. 1 minus 1 half plus 1 third plus 1 fourth. This series converges to natural log of 2. Now, what we do is we rearrange the terms. So we group them like this. Take two positive terms and one negative term, and then repeat that process. So now we have 1 minus 1 half, minus 1 fourth, plus 1 third minus 1 sixth, and so on. After simplifying and reorganizing, we end up um, with factoring out 1 half, and then from the original order, so our final result is 1 half natural log of 2. And this is how we know that this is a conditionally convergent series. So even though we're using the same terms, just in a different order, the sum will change. And the biggest takeaway relating to this topic is that conditionally convergent series depend on the order of their terms. In fact, there's the Riemann rearrangement theorem that says that you can rearrange such a series to get any value you want, or even make it diverge.
And so the basic idea of this is that it is very useful in determining whether a given series is absolutely convergent. And there's three possibilities within this. So if the limit of the absolute value of the ratio of consecutive terms of the series is less than 1, then the series is absolutely convergent and therefore convergent. If the limit is greater than 1 or equal to infinity, then the series is divergent. And if the limit is equal to 1, the ratio test is inconclusive, so we don't know if it's convergent or divergent. Now let's hop into an example of each of these. Example number 1. Negative 1 to the power of n times n squared over 2 to the n. And so here we can discard negative 1 to the n because the absolute value just cancels it out. And so we know that a to the n is equal to n squared over 2 to the n. And what we usually do is we plug in n plus 1 for n. That's why we get limit as n approaches infinity, n plus 1 squared over 2 to the n plus 1 in the numerator and the denominator, n squared over 2 to the n, which equals like the formula. And so when simplifying this, we know that dividing by a fraction is equal to multiplying by a reciprocal. So that's what we're doing when we're moving from step 1 to step 2. And that's why we would move 2 to the n to the top to the numerator, and we multiply that by n plus 1 squared, and we'd be moving n squared to the denominator where it's times 2 to the n plus 1. And now given this, we can just simplify as 2 to the n in the numerator is equal to 2 to the n in the denominator. So those are same terms except for 2 to the n plus 1. It leaves us with 2, which is why we get 2n squared in the denominator afterwards. And then in the numerator is just n plus 1 squared, which is n squared plus 2n plus 1. Now here we can just use the same coefficients that we learned in Calc 1. So it'd be n squared over 2 to the n squared. Using the same coefficients, we just use the numerical value, and that would give us 1 over 2, which is less than 1. And so by the ratio test, the series is absolutely convergent, thus convergent. Okay, now moving on to example number 2, series n to the nth power over n factorial. So here we know that a to the n is equal to n to the nth power over n factorial. And so we just substitute n plus 1 again into n. And that's why we get n plus 1 to the power of n plus 1 over n plus 1 factorial. And the denominator to the nth power over n factorial. And so when we use the reciprocal again, we'd be getting n factorial times n plus 1 to the power of n plus 1 over n plus 1 factorial times n to the nth power. And now when we simplify this, it's a little tricky, but we end up getting n plus 1 times n plus 1 to the nth power over n plus 1 times n to the nth power. And so this ultimately, we can just cancel off the numerator and the denominator, n plus 1, take that out, and we're given n plus 1 to the nth power over n to the nth power, which we can just get rid of by putting the exponent outside, which gives us n plus 1 over n to the nth power. And so this expression actually simplifies into e. And so because we know e is greater than 1, by the ratio test, the series is divergent. So now we move on to example number 3. Series 1 over n squared. Here we know that a of n is equal to 1 over n squared, and so we substitute n plus 1 for that. And that's why we would be getting 1 over n plus 1 squared over 1 over n squared. So same thing as the ratio test formula. And so here, when we simplify with the reciprocal, we just be getting n squared in the numerator, and then in the denominator, we're getting n plus 1 squared. And so when we express that, after expressing that, we'd be getting n squared in the numerator, and then in the denominator, we'll be getting n squared plus 2n plus 1. And using the same leading coefficients, n squared over n squared, just be equal to 1. And so because the limit's equal to 1, the ratio test, the series for this is inconclusive. So now we'll be moving on to the root test. Okay, so the root test, we use the root test when the nth power occurs. So again, there's 3 possibilities. The limit as n goes to infinity of the nth root of the absolute value of the sequence of a of n, where if the limit is less than 1, the series is absolutely convergent, therefore convergent. If it's greater than 1 or equals to infinity, then the series is divergent. And if it's equals to 1, the root test is inconclusive. And quick disclaimer here, if the limit is equal to 1 in the root test, don't try to ratio test because it will also be inconclusive. So moving on to examples. Example number 1. Here we see that a of n is equal to 1 over 5. And what we do instead is we just plug in directly into the formula of nth root of a of n. And so we just get n root of 1 to the 5th power of n, and because we have the nth root and the nth power, those just cancel out. So we just be left with 1 over 5. And we know that 1 over 5 is less than 1, so by the root test, the series converges. Now, moving on to example 2, 3 plus 5 to the n over 2 plus 3 to the n to the power of n. By using the root test, we can express the nth root as an exponent of 1 over n as its power over index, where we have the index of n, which is the denominator. And so we can express this using the exponent of 1 over n. And so we'd be getting the limit as n approaches infinity, 3 plus 5n over 2 plus 3n to the power of n to the power of 1 over n. Again, we'd just be canceling out the powers of n, 1 over n. So this would just leave us with the limit as n approaches infinity, 3 plus 5n over 2 plus 3n. And recall, we can use leading coefficients to find the limit here, which would just be 5n over 3n. And this just leaves us with 5/3. And we know that 5/3 is greater than 1, so by the ratio test, the series diverges. Now moving on to this last example, it's a harmonic series, where it's 1 over n, and the limit as n approaches infinity of 1 over n to the power of 1 over n is just the same thing as the nth root of a over n. So when we express this, we get that limit as n approaches infinity of 1 over power of 1 over n, and then the denominator n to the power of 1 over n, which just leaves us with the limit as n approaches infinity of 1 over n to the 1 over n, which is actually known for equaling 1. So the limit here is equal to 1, and so by the root test, the series is inconclusive. Thank you, and I hope you learned something within this.